Welcome everyone to the FEM at LLNL seminar series. As Anyo mentioned, we host this once a month and try to bring in some interesting talks. Today our speaker is Dr. Som Dutta, who's an assistant professor at the Mechanical and Aerospace Engineering Department at the Utah State University. Prior to that, he completed his master's and PhD at the University of Illinois in Urbana-Champaign. Som is an expert in studying complex flow and transport phenomena using high-fidelity CFD models that often require use of large-scale HPC platforms. Some of the diverse range of phenomena he has studied include the mechanism underlying drag reduction by shark tentacles, dispersal of oil and contaminants in oceans, fundamental dynamics of moving bodies in stratified environments, and transmission of airborne pathogens through aerosols. So before I hand over the ball to Som so that he can tell us about his interesting work on COVID-19, I want to mention a fun fact about Som that he was way ahead of his time and got into machine learning in 2009, way before it was cool, and all of us tried to get into it.
Actually, not even 2009, 2007, 8, when I was an undergraduate. Okay. Yeah, but doesn't. My advisors back then told me that I should learn fundamental fluid mechanics and math better before I get back to doing machine learning. So yeah, thanks, Ketan, for a kind introduction, and welcome everybody. So I will get going. COVID is I think you all might have heard that President Biden is about to declare by the start of summer that COVID emergency is over. And but we all went through this pandemic, and what I will be showing is some of the work we did and then I also will tell you why we need to continue to do this work, not just for COVID, but some of the stuff we learned has implications for future pandemic if it may arise, or even for indoor health and other things which we humans face in our everyday life. So this work wouldn't have been possible but for the bunch of different collaborators. Some of them I mentioned here, which includes Ketan, who is part of your team, and of course also contribution for some of folks like Paul Fisher, Neil, and Misan, whom some of you might have met and come across, and also Ramesh Balakrishnan. We also worked together a little bit a couple of years ago. So what I'm showing here is a bunch of is an isosurface of all the regions. So this is a flow inside in a relatively small room. You could say a hospital room, a 3 by 3 meter by 3 meter kind of almost a cuboidal room, and the flow in that is around 6 ACH, which is actually higher than what you get in your offices and your homes. But what it is, the isosurface is showing is all the regions where the velocity, the vertical velocity is higher than a small number, which would allow small aerosols to be suspended. And this is one of the first animations. When I started studying this back in 2020, this is the first animation we made. And I still keep this to show that, because even this simple thing starts to show that in a flow in a room, which we might think is a uniform and it's completely homogeneous, it's actually a pretty heterogeneous flow inside an indoor setting. So my goal has been for this project has been to accurate prediction of virus loading in the indoor environment. And when we started, quite a bit of things were known by people who have been studying it, like especially people who have been studying influenza before COVID came. But most of the things they'd always talked about was fomite-based transmission. That is, you cough or sneeze, and then those droplets fall on you, and then that's how viruses get transmitted from one person to the other. And that's the reason behind that this initially we had this 6 feet thing, right? Like everybody should be 6 feet apart from each other, then we will be safe. But we very quickly within the first year of COVID, we found that that 6 feet is not enough. And why isn't it enough? The basic thing is, and I built this cartoon, and the what I'm trying to show through this little cartoon is most of the aerosols and droplets we release, unless we are coughing or sneezing, are actually less than 5 microns. And when those droplets and aerosols, and I will soon show a little graph which will show how much time a small aerosol stays up in air. But we never earlier we were not considering the turbulence present in the room due to various things, and these various things include not only the airflow in the room due to your HVAC system. Actually, the airflow can also be induced by our own body heat, and I might show that animation of a body heat induced plume inside a room later in the talk. So with this idea, we started looking at it, and Ketan also got on board, and this is early 2020. But before that, and it became pretty obvious that what are the different modes in which transmission happens. So when there was this famous paper by Lydia Barubia from MIT, and she mentioned through her experiments that 6 feet does not work. And she showed that even a normal cough and sneeze could take aerosols up to 7 to 8 meters. And then soon cases like the transmission in the Korean restaurant started to be talked about and trickle in. And that in where it was found that people got transmitted not when they were sitting at the same table, but it was basically when they were sitting downstream of an airflow. So it started to get obvious that we need to understand, if we need to understand and predict transmission, we need to understand what are different things happening at different scales. That's why in the title of my talk, I talk about scales, because at the end of the day, that's what matters. I will talk about up to 3 different scales at which we are predicting transmission or risk of transmission from COVID-19 or any respiratory diseases that is transmitted by aerosols. So if you see the plot on the left-hand side, so what is plotted is for different aerosol sizes, say going from 1.7 micrometer to 167 micrometer droplets. So usually when we talk, the aerosols we release are about 1.7 micrometer to 5 micrometer. And on the other hand, coughing and sneezing is more like 20 micrometers to 200 micrometers. And what we can see is this is just plotted based on the fact that there is no background turbulence or flow. If you just take the drop of the aerosols, and we see that how if we start from a height of 2 meters, how long it will take to reach the bottom, and for how bottom of that is the floor of the room, and for how long it will stay up there. What we find is a 5 micron aerosol stays up to till a height of 1 meter for almost 20 minutes, and it could stay even longer. And a 2 micron aerosol, if it does not hit anything, can stay up in the air almost forever. It takes forever for it to come down. And to that, if you add the background velocity of the flow or turbulence, as I was showing in this animation at the start of my talk, we could see that very easily that in all probability aerosols will remain in the air for much longer, and that's why there was this whole aspect about then transmission beyond 6 feet. So when we started to think about how to model this, we had to think, what is the fidelity we go with, right? And we were not the first ones. When I say that first ones, so first ones in the context of COVID, but there have been people who have been studying flow inside indoor settings for a while, for a long time. So I looked at that literature. We looked at that literature, and we found that uh, there was no agreement about which is the best turbulence closure if we were doing RANS-based or time average turbulence closure. And it got obvious that we will have to understand the physics and to predict accurately, we will have to do turbulence or eddy resolved simulations. That's why for under stuck to of the transmission phenomena. Now, by the end of the talk, I will tell you why I think it's not a good idea. And but let's go and see what we learned first from doing these direct numerical simulation and large. So the first study we did with some collaborators, and Ketan was also involved with some collaborators from Spain, was we wanted to conduct a DNS of a cuff. Until then, nobody has actually, this is the first DNS of a cuff, of a cuffing event. After this, some other folks have tried it or have a high fidelity alias, but this is, in my opinion, the first DNS of a cuff. And these are fluids. So what this setup is, essentially, we model the cuff like basically a flow that ramps up and ramps down. So this is like a small cuff, not like a big cuff. The Reynolds number of the flow is around 6,000. And we actually wanted to do a 12,000 Reynolds number cuff, but the resolution requirement was getting too high. So we had to ramp it down. The other thing we faced was, because this was an unsteady flow, because if you see, there's a ramp up and a ramp down. So W0 T is defining the inlet velocity of the cuff of this flow that is, which is basically modeling the flow through a human throat with a little bit of bump to induce the vortices which comes out when humans are coughing or breathing. And an unsteady simulation is always harder to converge to the pressure solve for an unsteady flow. So we basically had to ramp down our Reynolds number so that the resolution requirement is not so high, and we could converge to a good solution. And essentially, we were solving the incompressible Navier-Stokes equation coupled with an equation to model the temperature. And the temperature is important because the human body, or the flow that comes out of a human body, is at a temperature of around 37, 38 degrees Celsius. Whereas most of the time, the comfortable temperature in our indoor settings is around 25 degrees Celsius, or sometimes even lower. So there is a difference in that temperature, and that actually induces a buoyancy-driven upwelling, which I will show. What we also did was we modeled the aerosols which were coming out, and we basically tracked the velocity of the particles of the aerosols as well as the diameter of them, because we wanted to take into account the effect of evaporation and how much effect does that have. So basically, we modeled this using our the spectral element-based Navier-Stokes Solver NEC 5000, and we basically used a third-order semi-implicit time-stepping scheme, both for our for time-stepping of the Navier-Stokes, but also for the aerosol or the particulate equation. And we basically had 300 million computational points, and this simulation took around 5.2 10 to the power 5 CPU hours. Right. So a lot of people in the audience are exascale folks. So this is nothing, and I agree. But the folks we were working with back then, we had certain limitations of how much CPU hours we had access to. with the modern NekRS and the FEM codes, this could be blown out of the water in maybe in 2 days. And we basically looked at different size aerosols from 4 to 256 microns because we wanted to look at the aerosol sizes. And there was around 200,000 particles which were tracked. So what I'm showing is essentially the isosurface of the cuff which is coming out. So what you could say here is the first animation, the first on the left-hand panel is a side view. So basically you are cuffing and what would the cuff look like from the side. The right-hand panel is the front view. That means, say, if you are standing in front of somebody who is cuffing towards you, which you won't want, I'm sure. And then, and this is the top view of it. And what this beautiful coherent structures show is that that even a simple cuff is a pretty complicated flow. The important feature I want you to focus on the fact that after the cuff has come out, which comes out as a jet, due to the difference in temperature, there is an upwelling of part of the aerosol cloud, and you see it starts to go upward. So there is one part that basically goes off at the front end, the lobe, and then there is the second part which basically starts to go up due to difference in temperature between the background and the cuff. So when we looked at it, if you look at it, the velocity, magnitude, and temperature of it, and through the whole transient of the cuff growing and coming down, what we see is what I was mentioning, that that essentially initially it starts like a jet, and then it lets off a little lobe of fluid which goes faster and further than rest of it. But most of the physics is actually, the little long-term physics is governed by this buoyancy driven plume, as you can see. And we basically, this simulation was of about up to 1.5 to 2 seconds after the cuff, somebody has cuffed. So now if we look at it a little bit more in a quantitative manner rather than a qualitative manner, what we see is that the temperature of the puff of the front and the vertical velocity, it has a velocity and it monotonically increases, and then it becomes really slow and freezes and it's not. And one of the reasons to do this DNS was we wanted to compare against some theoretical works like Lydia Barubia had was. So the main thing I wanted to focus on this slide is that one of the reasons to do the DNS was we wanted to see how different actually the flow is from what the theory says. So we just compared against the theoretical. There are these formulas which you can use to predict the track of the centroid of the gaseous puff, which comes out when you are puffing. And what we found was that the general track, what the DNS was showing was quite a bit different from what the theory said. And the main thing was everybody was interested was what is the aerosols doing? What are the particles doing when we are coughing? So what we are plotting here is two cases: so basically having the evaporation turned on and the evaporation turned off, and we wanted to see how much evaporation has an effect on tracking these the transient of these aerosols. And when we added these things up, so essentially what we tracked was between 4, 8, 16, and 32 micron aerosols. We wanted to see where they landed depending on if you have evaporation turned on or turned off. So the dashed line is the location, the mean of the location of the aerosols of a particular size if you had evaporation turned on, and the solid line is when evaporation is turned off. And what you could easily see is that when you have much larger aerosols or droplets, it doesn't matter if you are considering evaporation or not, they always kind of track the same way. But if you have aerosols of a certain range, that is essentially somewhere between 64 micron to around 16 to 8 microns, there's a particular big difference in where the aerosols actually, your prediction of where the aerosols will land, if you had considered evaporation or not in your simulation. So it kind of gave us also a good overview of what to do as we moved on to the room scale simulations. For the year of time, I will just quickly move to the room scale simulations. So for the room scale simulations, what we did was we considered a 4.2 by 3.3 by 2.2 meter room. And we basically had an inlet and an outlet at the diametrically opposite location. We chose this because this is one of the room which people have, or one of the example cases people had simulated back in 2016 or 17 to study in general transport of aerosols in the indoor environment. And what we did was we wanted to pay particular attention to the turbulence we are resolving. So one of the things we made sure was that the turbulence that comes in through the inlet, and this is something a lot of literature has been published in the last few years. This is something I have found people are not doing. People are mainly putting in laminar flow through their inlet, but the flow that comes in through your HVAC is turbulent. So if you really have to get your turbulence correct, in my opinion, you have to have a fully turbulent flow coming in. So we paid attention to that, and we ran three different HVACs rates, 4, 6, and 8 ACH. And this is essentially how many air changes per hour. Usually in office spaces, it's more closer to 4 ACH or even lower. And 8 ACH is, say, something like a chemistry lab or even a hospital. So, and we again used the spectral element based discretization. So essentially we used NEC 5000, and we also added 500,000 aerosols, and the number of computational points to resolve this simulation is around 100 million computational points. So what you could see is the fact that this is an instantaneous field of how the flow looks, and we are plotting temperature within the room. And what you could see is even at a statistically steady state, the temperature, and that's kind of expected from turbulent flow, right? The temperature throughout the room is not uniform. You always will get some zones where it will be slightly higher or slightly lower than what you expect to be the uniform temperature. What it also shows is that there is a definite structure of the flow within this room, which is induced due to not only the shape of the room, but it's also induced due to the location of the relative location of the inlet and outlet of the HVAC system. So, so what I'm showing here is, so one of the things we wanted to in particular study was what is the dependence of if you are releasing aerosols at different locations within the room, do they all behave equally in the sense, because there was all this literature about well mixed box. So what people say is that, and if you look at lot of literature, even on COVID in the last couple of years, people assume that inside the room doesn't matter where somebody is releasing their droplet or aerosol. It doesn't matter. Everywhere it will be a well mixed room. So it will be a well mixed box. So when that is happening, so one of the things essentially is the important thing what we wanted to see was what is the effect of the locations of release of these aerosols. And what we are plotting on the right hand side is on the corner is we are basically tracking how many aerosols or particulates have gone out depending on their initial release location. So what we are seeing is so P1 or essentially the red one is the aerosols which were released closest to the outlet. And what we would expect is that, okay, depending on how close one is to the outlet, our aerosols most probably will just be based on that. Yeah.
So I was wondering, you just mentioned, and maybe you were building towards it, that it's important to have our flow turbulent, or like the inflow profile turbulent,
Right.
instead of laminar, which most people assume. Can you elaborate on
Why?
like what are the, like, what's the impact?
So essentially, if you are putting in a laminar flow inside, and then you at the end of the day your aerosols are so small, they're essentially they get transported around using small scale fluctuations in the flow, right? And so and then because apart from the large scale structure within the room which takes the aerosols one way or the other, the the mixing, the other big factor of mixing is essentially turbulence.
Mm-hmm.
So if you do not resolve the turbulence correctly, uh, you will, in my opinion, you will not get the accurate accurately you will not get the accurate prediction of where the aerosols will land. And this is basically primarily due to the fact that the aerosols are really small, because at the end of the day they will follow even the smallest fluctuations you see in the flow. So
Right.
if you do not have that, then if you haven't considered that, it will not work perfectly.
Right. Makes sense.
I guess I have another question related to this, the size of the droplets.
Yeah.
I mean, is there any sense of, I mean, from the COVID community, like how many droplets or how much you need to be, like have a 50% chance of being infected or something? Is there any data about that?
Right. So this is a great question. So what you are alluding to is what we called dosage, right? So essentially, how many droplets or aerosols of a particular size do you need for somebody to get sick? That's basically what you are essentially asking, right?
Right.
Yeah. So the unfortunate thing is there has been uh, some work along those lines, but the problem is that there is this whole thing that is happening, which is we have a source and we have a sink, and then there is the whole transport of the aerosols. And because the COVID has been is such an infectious disease, we have tried, we have not done these things like trying to see, because we cannot, humans are not guinea pig, right? We cannot give them a certain number of aerosols and check if they are falling sick or not. So those kind of studies have not been done. But what people have tried to recognize is, or try to figure out is that what kind of aerosols one is releasing when they are sick at different points in their in their 14 days time, or when they're asymptotic. And what they have also tried to back calculate from events they know, like say these super spreader events, they've tried to back calculate that, okay, what could have been the dosage, and make some conclusions out of it. But this particular quantified way, and I would love that too, because it will make prediction of if somebody will get COVID or not, much more easy, accurate, but it's to an extent at this point of time not possible unless we create this beautiful digital model which basically takes care of everything, right? Like generates the aerosols, transports it, and also figures out everything that goes on related to the virus, to how it affects humans. And the other big factor is the same amount of dosage will not be the same for every human. So it has been found that in the same home, one family member got COVID, and then instead of all the 4 getting COVID, only one other got the COVID. So there is no hard and fast. There's no hard and fast rules about human transmission, which makes this thing very difficult. So yeah. So then what I'm plotting here is what I was talking about. That so essentially these are the 4 locations: P1, P2, P3, and P4, from which the aerosols are being released. And we are looking at 3 different views. So again, one view from the top, one from the side, one from the front. And what we would have expected when I started looking at this, I would have expected that, okay, the aerosols which are released closest to the outlet should get out the fastest to P1, and then P2, P3, and P4. But interestingly, what we found out was that actually aerosols which were released at P3, which is in the center of the room, were the ones which least number of them went out of the outlet. So essentially, it goes on to also the point that even in a simple room, this is an empty room we were simulating, right? There was no complication of furniture or humans or anything being there. We are just releasing aerosols and we were just tracking them. And these are, by the way, these are 5-micron aerosols we are talking about. So relatively smaller aerosols, which basically we release when we talk and breathe. So so this gave us, and then what we looked at was, depending on the size of the aerosols, we then basically did the simulations for 4 and 32, and then we had a point, we have a really small aerosol size we tracked to. And what we found was that there is a mix, and we basically tracked how many aerosols went out of the outlet. And we kept on cumulatively tracking, and we tracked till it reached some sort of an asymptote. And we found that, of course, the 0.5 aerosols went out much faster, but the 4-micron aerosols if you see, the percentage swept was almost consistently, there was a consistent gap between locations for the 0.5 micron aerosols. But for the bigger aerosols, actually, the smallest ones were the closest to the outlet were swept out much faster compared to the ones further away. And this is because of the fact that bigger the aerosols, it has also got the tendency to go and hit the floor, right, or stick to something else. So that basically made the once we went to larger aerosols, the amount of aerosols going out of the outlet became smaller and smaller. So the major things to take from a computational perspective is these simulations took substantial computational time. So 1.5 minutes of simulation time for this room scale simulation took about 768 node hours on the Frontera machine at Texas Austin, which is around 50,000 CPU hours. And so that means if we have to simulate somewhere between 30 to 60 minutes, which is what you need for these things to reach a statistically steady state, and we need around 31,000 node hours. And then add to that what I was talking about, what Ketan was alluding to, that in order to get the turbulence correct, you have to run it without aerosols or without particulates for around 50,000 node hours for it to reach the turbulence structures you want it to have. So essentially, these each simulation takes around 100,000 node hours to give you results on which you can say that you can scientifically say that, okay, these are believable. So these are very costly simulations. So the big question is then, can we keep on using these simulations to, because every scenario we go to and everything, every room is different, every event is different. So is this the way out? So we cannot keep on doing large eddy simulations or even RAM simulations for each and every case. So I was working with a team of engineers and scientists from NASA and Signature Sciences. And this was part of this volunteer group called Biotechnology. And we started to think from the other end of the, again, also from the other end of the scale. That means, can we build tools which are really fast? It does not have to be perfect. It does not tell where the aerosols all land and everything, but can we improve on the existing state of the art and can make fast prediction and in heterogeneous environment and give you a risk of transmission? And we are happy to say that we came up with this tool. We call it CEAT. It's called COVID-19 Exposure Assessment Tool, and this got published last year in Science Advances. And the beautiful thing about it is it's basically based on a bunch of equations we derived. And I can get into the equations if you want, but for the brevity of time, the interesting thing is that the whole thing runs on a PDF. So basically, it runs through a JavaScript. So you can download the PDF and you can basically put the different things the way, say, if you are organizing an event, you can basically put in all these things. Say, what is the room size, how many people are attending, where it is where you are attending it, what is the size of the room, the airflow rate, and even some information about how the local condition is. So maybe if you are in California compared to Louisiana, your your risk might be different because the rate at which people are infected in every locality is different, right? And then we also consider effective vaccination based on all that. But in my opinion, and maybe I'm saying this because I was involved with the fluid mechanics part of it, this was one of the first models, and I don't know if there is one after that, of the scale which runs so fast, which considers both near field and far field effects of transmission together. And we did this based on this grid-like structure we did our calculations on, which accounted for not only transmission from somebody who is close to you. So we basically, what we are saying is we consider proximity in our calculation of transmission or exposure risk. And this is most of the other models, and I will show some comparison against that, which are essentially like the ones you might have heard by Bazant and Bush. They basically built one on top of the from MIT. They built on top of the Wells-Riley model. They basically assumed a well-mixed box. So most of the other models which are in the market now are for fast prediction. They do it on the basis of a well-mixed box assumption. But we already saw through the simulations from the DNS and LES that the well-mixed box assumption is not a good assumption. So we need to get proximity information in when we are doing these predictions. So we brought that information in this neat way in this tool we developed. And when we compared against known super spreader events, we compared against about 20 super spreader events. And let me just orient you quickly. So the way this tool works is risk one. So we call it exposure assessment tool, right? Because what that tool gives you is how risky is whatever you are doing. So essentially, a risk of 10 to the power 0 or risk of 1 is somebody, if I say Nick's sit opposite to Ketan across a table, and if Ketan has COVID, how risky is that to me if both of us are not wearing masks? We benchmark that as our risk of 1. So anything that is higher than that, of course, if you are in that situation, you will not want to be in that situation, right? So you want your risk to be lower than 1. And if we have risk higher than 1 and higher it is, we know that that event was is a high risk event or was a super spreader event. So when we went in and took data from about 20 super spreader events, which were in the literature, we had good information about all the factors we consider in our model. We found that all of them fell within high exposure to very high exposure. And just to be sure that we are comparing apples and apples, we also went and compared against the Wells-Riley model and how well the Wells-Riley model does in those scenarios. And we found that our models, our square was around 0.93 to 0.88, whereas if we just used a simple well-mixed box Wells-Riley kind of a model, the accuracy of their prediction of somebody getting a COVID in a certain event was around 0.6 to 0.42. Now, what is the use of this? So basically, NASA Ames used this tool to inform organizing different events or meeting at their Ames campus. So this tool, and so if you look at the paper, if you want, I can send it to you. People actually have already used, and we include that data from NASA about how NASA went on to use that tool to basically inform if this event should be organized or not. And the other thing is this tool is also is endorsed by the American Hygiene Society. These are the people who care about how good your indoor setting is, and also the CDC. It's not endorsed by CDC, but was partially funded by CDC. So at the end of the day, what I want to end with the fact that where are we going with this, and how the scientific computing community, like the audience, I guess here, can help in this effort moving forward, because we saw that the computational these high fidelity LES and DNS simulations require a lot of computational resources. So the next step we are working on, and these slides, these numbers are from Neil Lindquist and Mason Min and Paul Fisher. And the idea is that we basically transition from running on CPU-based simulation to running these aerosols simulations on NekRS or GPU-based simulations. And some initial data they had shared, and some of you might be already familiar with this data. Sanyo, your team might be familiar with this data. What we found was that compared with the CPU, there was a drastic reduction in basically time required to solution when we move to the GPU, or when we basically move to NekRS. And this is essentially quite a big of a difference. If you see 277 to 3.6, this is almost a 60x difference. Now again, these data are for a box where the particles are uniformly filled with it. Of course, the simulations you saw, that is not the case. Your particles are not uniformly distributed throughout your domain. They could be converged to one side of the domain, but still, I think we should be able to get using GPUs. We should be able to get faster results. The other thing is I think is the long-term, slightly a long-term vision of this, and I will end this part of the talk with this. The fact that even the tool we developed, the CEAT tool I showed, is not perfect, because it does not take into a lot of different heterogeneities we didn't even talk about, which could basically throw off the prediction. And frankly speaking, we did so well, and I will be honest, we did so well in the prediction against the super spreader events because we knew those were super spreader events, right? So you can always adjust your model to try to predict well. Everybody who has done modeling knows those tricks. What is the future? The future is essentially somewhere in between. We cannot depend on high fidelity simulations or simulating each and every scenario, but I think we just cannot also rely on that simple tool that runs on a PDF. I think where is somewhere in between, and this is what I would love to propose is one is to first understand the turbulence better, because unless we universally understand, or unless we understand the universality of the fluid mechanics of the flow within these indoor settings, we can keep on making simulations of different settings, but we will not be able to make any good prediction. So that is one end, but we have to take all that data and basically do these lower fidelity RANS models and then improve the prediction of these lower fidelity models using machine learning. There was a talk in the series I saw by Ricardo Vinuesa. They are doing some great work at KTH on building these, trying to build turbulence closures using LES and DNS data. We are also actually doing the same, and I was just talking with Sanyo, with Paul Fisher, and some folks. We are also on that track to try to build turbulence closures using large-scale DNS and LES data, and then doing uncertainty quantification for it. So I think this has to, all that knowledge has to go into basically making these predictions better. So, and so that's kind of my end of my talk. I have a couple of slides about some other things we are doing in the group, but I will stop for questions if you have, and then I will, if we have time, I will show a few other things, some interesting things you guys might be interested in, we are doing in our research group.
I was wondering, so this CEAT tool you mentioned, it's quite interesting. What are kind of like what's the kind of data that went behind it? Because it seems like it's taking in these parameters which are very diverse.
Yeah.
I guess you need to somehow bring them together.
Yeah.
So
let me pull the equation that brings them together. So it's basically a probability-based approach, and if you see, so it's essentially a multiplicative factor, each one of them. If you see, so there is all these different things. So there is behavior and subpopulation. So there is a factor due to that. There is a factor due to so it's when we started, it started just for the basis of the flow. Okay, so this is the core equation we started with. You see, because it takes into account ventilation, indoor factor, and duration, and then we saw that okay, maybe we can keep on adding other factors in as a multiplicative factor to basically say that it is getting more riskier or less riskier, right? So if everything remains the same, if I know that my event is happening at a place where there are more infection, the infectious rate is higher, I know that there is a chance that an event I organize will also have a higher chance of somebody getting infected. So that is a multiplicative factor, right? If everything remains the same, each of the independent parameter is a multiplicative factor. This comes out of probability theory, essentially, right?
Right. Yeah, makes sense. And what are kind of the confines of it? For example, like are folks using it to plan indoor events, outdoors?
But so we can do outdoor events, but as soon as you do outdoor event, if you do look at this, what will happen is your risk goes down very quickly, because an outdoor event, if you have wind and it's known that in outdoors, COVID-19 transmission does not affect at all. So this is actually much more important for organizing indoor events. And actually in the paper, we point to some scenarios. So we talk about, say, if you are doing a Thanksgiving dinner in different locations, right? So how is your risk? So we basically say, and depending on number of people you have in your party, how many people are being masked and things like that. So we basically did a bunch of sensitivity analysis to chart that thing out.
Right, right. Makes sense. Okay. Yeah, this tool seems quite interesting. I see Zanio has his hand up.
All right. Thanks for this really interesting talk, Tom. Very, very interesting topic, very interesting work, very interesting results. I do want to follow up on the question that Keaton asked. So there is the really high resolution, what we believe to be the truth that requires HPC results, and then there is the tool, which you said runs in a browser. So it's obviously it's not doing the right simulation. What is the connection between the two? How is the high HPC results informing some of these factors here? And what is the kind of simplifications you have to make to distill a number or several numbers from the HPC simulations?
So at this point of time, this tool is not quantitatively informed by the high fidelity simulation, right? At this point of time, these were completely based on our general understanding of how flow is. But there's a particular one in which where the HPC and what we are learning from the turbulence models will have a factor. So when we are calculating transmission, we basically use this factor called dispersion coefficient, K, right?
Mm-hmm.
How well you calculate that is basically an open question. And this is what will be informed by taking high fidelity simulations. As I said, understanding the turbulence better, but also taking that data and coming up with a predictive tool which will be able to quickly tell what should be the K used depending on the size of your room and the location of your ventilation. Because those two are the main big heterogeneous factor: size of your room and the relative location of your ventilation. And essentially, the idea would be that we are able to do that as we go forward. We start to crunch these data and try to take out of it what we get is the dispersion coefficient. That's what matters, because at the end of the day, that is what will be used. Because if you want it to be a fast method of prediction, it still has to be something which solves the equations really fast, right? Something which does, but then to inform those factors, which are the dispersion coefficients, is where our HPC simulations will come in. And essentially, I think, and machine learning will come in to basically try to predict those things much faster and for a much diverse set of heterogeneous environment than what we were able to do using this constant K we use. Basically, we use a constant K, or basically a K which was just not a constant K. We basically made the K dependent on ACH, but we did not make the K dependent on the location of your inlet and outlet, right? But then that is very important, and that's where I think we need to go next.
But this is still a significant simplification that I'm sure it's useful. How far are we from showing up in the room, using the LiDAR on my iPhone to scan it, using the microphone to measure the speed of the air ventilation, offloading the compute to some cloud and getting results in reasonable time?
I think we are not that far. Frankly speaking, a steady state RANs can converge to a good solution pretty fast, or a potential flow solution can be converged to a relatively few seconds. So this is kind of, you are saying out loud what I have been thinking. I did not think about I did not think about using the microphone for figuring out how fast my flow is coming in. But
maybe there are other ways. I don't know. I just thought of the microphone as one way.
but
certainly you can scan the room with the LiDAR these days.
Oh, yeah,
and you can run in the cloud with GPUs from the phone, right? It's there.
I don't know if that product is an actual product, but there was some sort of things where Siemens, I was seeing this video, Siemens or somebody was showing a product in which you come in your room, you take photographs. So I think they were not doing LiDAR, but you take photographs of the 4 walls of every room has 4 walls, right? Or if it's in general, so you take 4 or 5 pictures of the room, and then basically it quickly construct together a model within, and then it gives you, and if you know where the inlet and outlet is, you can actually make a very quick prediction, and then you can basically improve on that using all the data from the HPC. So actually, you do not need HPC to make this fast prediction the way you are talking about, and that has to be the base of it.
Okay, cool. Thanks. Very interesting.
Thanks, Daniel. I'm sure we could write a proposal about doing this. I think it'd be cool if you could just, take a video with our phone, send it to the cloud, make a mesh to our simulation.
Well, the great thing about the stuff you guys are doing, FEM now runs on a cloud, right? So, yeah, and you guys have all the, but anyway, this is a different conversation to be had. If you guys are interested.
Right.
Yep.
Okay, well.
All right, yeah, does anyone else have any questions in the audience? Otherwise, Soumya, if you wanna take a moment to show us what you're doing, that's fine.
Yeah. So quickly, because I thought you guys might be interested, because California and like in Utah, we suffer from wildfires, and it's becoming a bit. So one of the big projects we are doing is actually, so wildfires everywhere it happens, you have these planes going around and dropping these retardants, right? And this is a video shared with us from USDA, because they basically certify these planes to go and drop these, which go in and drop these retardants to put out the fire. So we are actually working on a project now, and we have put in a NASA SBIR phase 2 to basically, we are working with a company to build a predictive tool to predict where this plume will land once it comes out of the aircraft. And the reason it is important is a more efficient and more accurate dropping mechanism will not only put out the fires faster, but so that will reduce the cost of damage from a fire, but it will also bring down the cost of dropping these retardants, because every time a plane flies and drops these retardants, it costs anywhere between 25 to 30,000 per flight. So and depending on where you are and how far the airport is. So we are pretty excited about this, because, and also the folks we are working with at their end, they are building this tool for flight safety, and we are coupling this retardant plume predictive tool with the flight safety tool, so that it could basically help the pilots to have better targeted drop off these retardants. So this is pretty exciting work. One of my PhD students is working. There are some lot of fundamental questions related to it too. So my PhD student is working on that. Apart from that, some of the stuff we are doing is we have this, as Ketan was mentioning, one of the other big focus on my research group is stratified flow, mixing and transporting stratified flow. And the implications goes from movement of submarines or movement of bluff bodies in stratified environment, in say under the ocean, to some interesting work we are doing related to the oceanic wind farms and what kind of turbulence and structures they generate, which end up mixing the ocean. And then, of course, we are doing some work at the Great Salt Lake about the lake. And of course, there has been a big. I have come back to machine learning, let's put it that way, after my grad school, once I became a professor. And there's a big push in our group, and we are doing a bunch of different machine learning related projects. One of the interesting ones, we are working with the Naval Research Lab to figure out if we can mimic fish behavior, fish swarming behavior using reinforcement learning. So I don't show a slide on that, but that's one of the more exciting ones. And finally, we are working on. We just recently published a paper in Royal Society Open Sciences, where we are looking at how we can build these surface features, because with additive manufacturing you can build a lot of different complicated surface features now, which we couldn't do 10 years ago. And this is allowing a new revolution in bio-inspired approaches for passive drag reduction. So that's kind of the other direction, other focus in my research group. So yeah, thanks.
Awesome. Thanks. Yeah, it's a lot of different interesting directions you're taking with your work. Okay, let's give Som another round of virtual applause. And let's see, unless folks have questions. Yeah. Okay. Do folks have any other questions? If
I just want to say this was really interesting. Thanks for coming, Sam. I'm sure this will stimulate a lot of discussions.